Hello! In this video, we're going to talk about the generalized uncertainty principle with some examples. So the generalized uncertainty principle says consider two Hermitian operators, say a hat and b hat. And then if you consider the product of the standard deviations of these two operators, if you were to make some measurements on them, then the product of the squares of those standard deviations had better be greater than some quantity, and that quantity happens to be related to the commutator between a and b squared. So this tells us if the commutator between two operators is non-zero, or more precisely, if the expectation value of the commutator between two observables, a and b, is non-zero, then the product of the uncertainties between a and b is also non-zero. The implication is that you can't then be in a simultaneous determinate state of both a and b at the same time. Or maybe said in another way, since a determinate state is also an eigenstate, so it has a definite value of that particular measurable. In particular, this means that the particle doesn't have a definite value of whatever observables you're considering, a and b, at the same time. Let's just use an example to understand what all of this means, to take it from the abstract and be a bit more precise. So let's consider the position-momentum uncertainty principle. If you recall, the commutator between the position operator and the momentum operator is just equal to I h bar. So the generalized uncertainty principle says that the product of the uncertainties of x and p has to be greater than or equal to 1 over 2i times the expectation value of I h bar, all squared. Well, the expectation value of a constant is just the constant itself. And so the thing inside the expectation value just becomes I h bar. You cancel some i's, and so then you get h bar over 2 all squared. The usual way we write this is by taking a square root of both sides, and then we say that the product of sigma x times sigma p had better be greater than or equal to h bar over 2. And that's Heisenberg's uncertainty principle. And so it just comes out of this generalized uncertainty principle. The meaning that we talk about for Heisenberg's uncertainty principle is that you can't simultaneously have a definite value of the position x and the momentum p because the product of those two have to be greater than or equal to h bar over 2. So they can't both, for instance, be 0. Of course, you don't have to just consider the position-momentum uncertainty principle. You can make up your own uncertainty principle. All you have to do is pick your favorite two operators, a hat and b hat, and find their commutator and the expectation value of that commutator, and you can make your own uncertainty principle. So let's look at an example of a different uncertainty principle that's not as famous as the Heisenberg uncertainty principle, for example. Let's look at an uncertainty principle between momentum and kinetic energy. So remember, kinetic energy is represented by the operator t hat. So we want to know what is the product between sigma p squared and sigma t squared, where p is momentum and t is kinetic energy. Well, we know that the product of the squares of those uncertainties had better be greater than or equal to the expectation value of the commutator between p and t. So we had better figure out what the commutator between p and t, or between momentum and kinetic energy, is. So let's write that out over here on the left-hand side. And actually, before we do that, we realize whenever we're talking about commutators or really even operators, they only make sense when they're acting on a wave function or on a state. So let me just insert a wave function there so that I know what I mean by p hat and t hat. I know that they're operating on something. So let me just write out what a commutator is. By definition, the commutator says that between p and t is that it is p hat times t hat minus t hat times p hat. You're just switching the order. And those are both operating on the wave function psi. We know what p and t are. We know p in terms of derivatives. And the kinetic energy operator we've seen before as well. We can write that in terms of derivatives, in terms of x derivatives. And so we write out the product p hat times t hat operating on psi minus t hat times p hat operating on psi. We get something that looks like this. We can simplify this considerably by distributing the derivatives through and moving the constants out front of each term. So let's do that. So when I do that, for instance, on the first term, I see that I have a minus sign. I have h bar cubed There's a 1 over 2m and an I downstairs. And the partial x goes through and combines with the other partial with respect to x squared and becomes a partial cubed with respect to x cubed acting on psi. For the second term, I actually get the same type of thing. I just distribute my second derivative through now and pull all my constants out front, and I actually get the exact same thing. So when I cancel the minus signs here, it turns out both of these terms cancel against each other, and I get 0 for this commutator between the momentum and the kinetic energy. Well, the expectation value of 0 is still 0, so now I can insert this into my momentum kinetic energy uncertainty principle, and I find that the right-hand side is 0. Taking the square root, just since it's oftentimes easier working with the sigma instead of sigma squared, then this tells me that I am allowed to, in principle at least, have simultaneous definite values of the momentum operator and kinetic energy operator. They both could, in principle, be 0, because 0 times 0 is equal to 0, which satisfies this uncertainty principle. Now, whether you can actually do that or not depends on the state that you're interested in. And so in the next video, we're going to look at details of different states and see in which cases this is satisfied, or saturated that is, and in which cases it's not.